Okay, this video we're going to look at the continuity equation and problems 26 through 30. I'm going to try to give you some helpful hints for the fluids competency. So number 26, it says a patient recovering from surgery is being given fluid intravenously. The fluid has a density of 1030 and 9.5 E negative 4 meters cubed of it flows in the patient every 6 hours per 6 hours. Okay, what we want to do quickly here is take 1 hour is 3,600 seconds. Convert that to meters cubed per second, which of course is our Q. This is our volume flow rate. And if we have the density, we know density is mass over volume, so it could be the mass flow rate over volume flow rate. And so mass flow rate will equal the density times the volume flow rate. So all we're going to do is get this volume, or this volume flow rate here, Q, take it times your density, and you should have your mass flow rate in kilograms per second. This is a mass flow, not just mass, so kilograms per second. That'd be problem 26. Okay, problem 27. So really what we're doing is we're using the continuity, and so volume flow rate somewhere equals volume flow rate somewhere else. And the way you figure out your volume flow rate is you take the area times the velocity. So the area somewhere else times the velocity somewhere else, that should be equal. So in this next problem, we have air is replaced in a 120 cubic meter room every 20 minutes. So I could do 120 cubic meters per 20 minutes. 1 minute is 60 seconds. So we'd convert that to, there'd be our Q. It'd be flow rate, volume flow rate, 120 cubic meters per 60 seconds, and you could figure out what that is. It says, what is the length of a side of the square centimeters of an air duct if the airspeed within the ducts is 3 meters per second? Well, volume flow rate is area times velocity. So we're going to figure out our Q. We're going to divide it by our velocity. We'll have our area. This is the area of a duct that's a square, and we're trying to figure out what one of the sides is. So once you figure out the area by taking this Q divided by the velocity that was given in the problem, you'll have your area, and you need to take the square root of that to get the side of one of the squares. Now this problem also says put that in centimeters, so don't forget to do that. That's problem 27. Problem 28, cross-sectional area of a faucet. Here's a faucet, something, and the cross-sectional area is given, so 1.8 E negative 4 square meters. The velocity is also given, 0.85 meters per second. So the water comes out, and what we're wanting to do is figure out what is the cross-sectional area down here. What is the area here? If the water has fallen a distance of 0.1 meters. Okay, so that means this area times this velocity should equal this area, which we don't know, times the velocity down here. So all we need to do to figure out this area is know what the velocity of the water is down here. And you should be able to do that. You know what its initial velocity is right here. You knew how far it fell. And so you're using a uniform acceleration equation. VF squared equals VI squared plus 2 gravity height. And so you can figure out the velocity down here, and then take this area times this velocity, this area times this velocity, divided by this velocity, and you'll have your cross-sectional area. Okay. Problem 29. A water pipe with a radius is given, connected to a shower head. So we have this situation here, shower head, and there's a whole bunch of holes here. And the velocity is given in this. We want to know what's the velocity coming out of one of the holes. So the radiuses are given of the holes and this pipe. So I'm going to take the velocity in the pipe times the area of the pipe, which would be a circle, pi r squared, and sorry, that's not the volume, that's velocity right there. Velocity times the area, pi r squared. And then that would equal the area of a circle times 12, because there's 12 of them, times the velocity. So you could plug everything in and figure out what this velocity is, which would be the velocity of the water out of one of the holes. That's good enough for 28 or 29, hopefully. Okay, 30. Kind of the same situation. The aorta carries blood, and then it goes into, like, capillaries. So the velocity, now the velocity and the radiuses are giving in centimeters here. That's fine. We're going to go ahead and leave it in that because it's on both sides of the equation, so it doesn't really matter. So the velocity in this is 40, the aorta is 40 centimeters per second. And then the radius is 1.1 centimeters. So all we have to do is do the velocity times the area in the aorta equals, and it gives us the velocity of the blood in capillaries, which I could put V, and the radius of a capillary, so that means I could figure out the cross-sectional area. We'll assume it's a circle. And then times N, because I'm going to have a whole bunch of capillaries. So I'll be able to put the V and the A in there. I'll be able to figure out what N is. If I divide this V and A by this V and A, I'll have the number of capillaries that we want, and it's going to be a very large number. Hopefully that helps you on problems 26 through 30, which is the equation of continuity problems.